Today's lectures will be dedicated to the study of the atom. You know, we saw some models as we saw the solution of quantum mechanics in using delta potentials. We saw situations that somehow looks like an atom, but actually it is not really an atom, right? An atom is something three-dimensional, is something more complex than an attractive delta function. But we place that for you to know that a kind of singularity can hold the particles around it in a quantum sense, creating what we call bound states. But we know that the atom is where the bound states really exist. In fact, understanding the atom, how are the levels of the electron, how is the distribution of charge and everything, is what was one of the important challenges to understand that generates quantum mechanics, right? So if we cannot explain the atom, we cannot explain the unit that makes everything around us. So, okay, so after seeing the basis of the quantum mechanics using models, using one-dimensional type of examples, but they are good, don't think they are bad, we now are going to the really one electron atom, the hydrogen atom, which is the simplest atom we have. And we're going to solve it. We're going to solve explaining to you. We're not going to go in very detail about the equations, but we're going to solve giving some of the steps that is done to solve the problem. But we want more than explain how to solve, which is basically solve the same equation we had before, is explain what the solution means, right? Give interpretation, give some physical insights for the solution. So we can use it for many other things. Okay? Okay, very well. So today we're going to see the what I call the electronic orbitals for an atom. And when we have an atom, we have to start by saying that the atom has an electron. So we have an electron, and we have the nucleus with positive charge, and this is 3D. So it's very hard to solve the atoms in 2D and then extrapolate to 3D. And the reason for that is the way that the degrees of freedom on the energy or in the Hamiltonian, you know, they are distributed and how they are distributed. Because now, instead of single momentum, we have three components of momentum. Now we can have angular momentum that can have many directions in the space. So everything is important in the solution. Let's start by remembering the Schrödinger equation. And you remember the Schrödinger equation? We wrote many times that in one-dimensional, minus h bar squared divided by 2m times the second derivative in the position of the function plus the potential times the function is equal to the energy times the function. This is the time-independent Schrödinger equation. But this is in one-dimensional, where the derivative of the wave function gives you the momentum. But now the momentum, because it has three components, you know, the momentum square has three components, and this term here, it gets to be the Laplacian. If you remember, the Laplacian is the sum of the three second-order derivative of the function. So we are adding the component in x, y, and z. And the potential now, as you know, the atom has as potential the Coulomb potential. So we have 1 over r as the dependence of the potential times the charge of the electron square. And normally the charge of the electron is because of either the nuclei or the electron, they have the same charge, and the products divided by the distance is the potential. And everything we want to determine is the energy of this equation. So, of course, in these conditions, with this three-dimensional isotropic potential, which is the Coulomb potential, we must discover basically what's the wave that fits in this configuration. For what values of energy we can fit a wave in this configuration. So this is basically what we're going to solve, right? And this is normally what we call the, if this is a generic potential here, I already put the Coulomb potential, but this could be a V of R. And the R can be dependent on the vectorial R, which means depending on the angles itself, right, or themselves. So this is called the three-dimensional version of the Schrödinger equation. So we are now dealing with a particle that can have a freedom in the 3D space and is attracted by this force, which is the positive charge in the nucleus. And we want to solve that, right? And when we say we need to solve that, we want to give an answer for the question, how is the spatial wave? How is the spatial wave distribution for this electron? How is this electron able to live if it is a wave, if it is in the quantum mechanics context? How is the wave that represents the electron here? So we are looking for a wave function that depends in three coordinates. We can express this in x, y, z, or normally we prefer to express in the spherical coordinates. The spherical coordinates has the r, the theta, and the phi, which is the zenithal and the azimuthal type of angle in this configuration. And believe me, this is the best way of representing the atoms using the spherical coordinate, because the potential has spherical symmetry, right? It's only depending on r, and then it's much simpler to express the solution in terms of those coordinates. And of course, we're going to have components of energy distributed in all those coordinates. Now, so this is the function. We're going to express the Laplacian in terms of spherical coordinate. You can see in any book. You have a sine of theta, 1 over sine of theta. You have the second derivative of theta with respect to the function, and so on. And then we have the phi dependence in the Laplacian. But you know, the technique we can use it to solve the problem is admitting that the energy here can be separated, the terms here can be separated. We can have an equation fully with the radial part, an equation fully with the theta part, and an equation fully with the phi part. The three coordinates can have their own equation. And how is that done? Well, we can do that by making a separation of the solution. So we can start by saying that the solution is a product of three functions with three different dependencies. The first one depends on the radius. The second one depends on the theta. And the third one depends on phi, which are the three spherical coordinates that, as I explained there, represents the position of the electron. So what we have to do now at this stage is substitute in the Laplacian, put all the dependence of the angles and the variation with the angles of the wave function, and substitute the wave function by this product. And when we do that, it turns out that we're going to get a sum of three terms, one that I can make everything depending on the radius, one that depends on the theta, one that depends on phi. And because this has to be valid for any angle, they must be independent. They must be like a constant type. So when you do this procedure for the solution, which is not tedious, but it takes some time to do, we end by having 3 equations. And constants will appear in the solution. And I already put the constants in a convenient way. Okay? So, making the substitution in the Schrödinger equation, we find that the phi solution, which is the solution that's depending on the coordinate phi, is given by this equation. This is a very nice equation because we know how to solve already. We know that this is a oscillatory function. We know that the solution for this must be something like exponential of I m phi. For the theta, we get a solution that somehow depends on those constants. So there is a constant here that's called ML, I call ML, and that's going to appear here. But because we make that part of phi equal to a constant, you end by having the constant on the theta too. So here we get the same constant there, plus a new constant that we call L. And we wrote this constant as L times L plus 1. Right? And then finally, for the radial part, we get another constant. So we not only have in this equation that constant that appears in theta, but also the other constant, that's the energy. It's the other parameter. And those equations now, so it's like splitting out the 3D equation in a collection of 1D equations. And there are many ways of solving this, right? And this is basically, when you solve this, you get conditions for validity of the solution in terms of those constants. So you're going to see that those constants, they must have special values, which are the quantum values that determine the solution. So that's what turns out that we reduce the Schrödinger equation in 3D in a couple of equations with separate variables in each equation. This one depends only on r, this depends only on theta, and this depends on phi. And now we can solve them. The first one is trivial to solve, right? The solution in phi. I just want to remember that phi is the angle in the plane here by the projection of the vector, the radial vector, right? So this is phi. Okay? Okay, so we're going to take these equations and now we're going to solve them. And when we solve them, we're going to get, as I told you, conditions that hold together those constants and the energy. And that will give the origin of the atomic quantum numbers that we normally learn. The orbital quantum numbers, the magnetic quantum numbers, or the projection of the orbital quantum number, and the total energy of the system with the principal quantum number. Okay, so let's start by solving the first equation, which is the equation in phi. And we are looking for a function that twice the derivative repeats the function and has a constant on it. And we already learned that this solution here gives you the complex exponential type of solution. Okay, so we're gonna try now to do this. So we're gonna keep this in mind, those equations, and we're gonna use each time, anytime we need. And let's go for the first equation. The first equation is the equation in phi. The solution is a well-known solution. You know, phi has to be like a constant exponential of I ml phi, right? And because if I take phi and I give a turn of 2 pi, I get back to the same point. So I need a solution that repeats itself each time I add 2 pi to the angle. For that to be true, if you say that this has to be equal to A, exponential of I ml phi plus 2 pi is because exponential of I ml 2 pi has to be unit, right? So the only way for this to be true if exponential of I ml, which is this constant here that we put in the solution, times 2 pi is unit, because then we don't change. And for that to be true, the ml has to be an integer, positive or negative. So we already got, because of this boundary condition, we got values for the constant ml. So ml can be only 0, plus minus 1, plus minus 2, plus minus 3, and so on. And this is a quantum number, means that this number, the solution will exist when this parameter, this number that appears in the equation, is one of those numbers. And so this is one of the quantum numbers that appear, and it's called magnetic quantum number. Right. Now we go for the solution of theta. The solution for theta is an equation with many terms. But this is well studied in mathematics. This equation is well studied in mathematics. And this is the solution for the so-called Legendre associated functions or polynomials. And for theta to exist in here, for having solution, you cannot have any connection between L and ML, but must be a collection that says that for the solution to exist, ML must be bounded, not only being an integer like here, but not any integer, must be bounded to plus or minus L. So you see, here we found that can be anything, an integer positive or negative number. But here we find that can be an integer positive or negative, but ending in L. So L must be also an integer. And L is called the orbital quantum number. So the limit of ML is the orbital quantum number. And we're going to already make some physical association with it. And then comes the equation in R. The equation in R is an equation that has the second derivative too, but has the L in here, right? So that must be some connection between those constants for the solution to exist. In fact, we find out that the solution for this equation are the Laguerre polynomials. And the Laguerre polynomials are functions. You know, we're not going to put explicit the functions, but we're going to put graphically very soon. And the Laguerre only exists when the energy is given by this term. Is depending on an integer number that can be 1, 2, 3, 4, 5, and so on. And the energy will depend on this principal number, and this is called principal quantum number. So you see, we got three different numbers, integer numbers, that determine the solution. And those are quantum numbers because they vary by integers, by integral number, and each collection of those numbers determine one function, is what determine what we call one state for the atom. Basically, the solution of the wave equation provides us naturally the conditions in which the solution exists. And the solution exists when we have a kind of relation between those numbers, and they can have specific values only. This energy is called the spectrum energy of the atom. And that's what's going to give you the origin of the energies of the electron. And you see, here does not depend on L and M. depending only on n, but somehow L and M will be bounded by this n. We cannot have any L depending on an n. Given an n, which means given an energy, we can have only a few values for this L. And having L, we have only a few values for the n. And that's how we generate the quantum numbers and the solutions. Okay, so L, if you look when the solution exists, you're going to find out that L, the value of L, is bounded to n plus minus 1. So L can have any values, 0, 1, 2, 3, and so on, until n minus 1. So for a given n, we have a collection of possibilities for L. And for a given L, we have a collection of possibilities for ML. And those are the quantum numbers, and those are the numbers that will determine the solution, and they have a physical interpretation. So basically, solving problems in quantum mechanics is when the solution exists, will naturally give us the energy, will naturally give us the information about the system itself. So by solving the Schrödinger equation for an electron that is bounded by a Coulomb potential, which is the atom, we find out that we need 3 quantum numbers to describe the solution, even though at the moment the energy only depends on the principal quantum number. And the principal quantum number can be 1, 2, 3 and determines the energy. This determines the energy at the moment for this type of atom. Depending on n, we can have different L's, and L is guarantee the existence of the theta dependence, which is the things that goes around, right? Goes around crossing the plane. The theta is the angle with the zx. And for a given L, if L exists, there is also possibilities for ML, which is called the magnetic. This one is called the orbital quantum number, and this is called the magnetic quantum number for reasons that I'm going to explain. Now, I need all the numbers to characterize one specific wave function? No, I need a collection. So actually, what's going to characterize a solution is a collection of n, L, and ml. These 3 numbers should characterize the existence of a solution. And each collection possible of those numbers, if n equals to 1, L can only be 0 and ml can only be 0. So that's it. But if n can be 2, then I can have 0 or 1 for L. Therefore, I can have 0 or plus or minus 1 for ml. So I have more and more distributions, more and more functions for one energy. When I have more functions with the same energy, we call degeneracy. So the hydrogen atom, in this approach, considering only the Coulomb potential, is very much degenerated. So it means I have many solutions with the same energy, right? And this will be solved later on. Now, we want to give it a physical interpretation or physical visualization for the quantum numbers. And to do that, we have to start to look to the energy of the system. So let's look to the energy of the system. When we write the energy, we know what's the energy. It came out from the radial function. We have a radial part. This is the total energy. What came out in the solution of the radial equation that gave us this value of the energy is the total energy of the electron. It's not only the energy in one part. It's the total energy, because that's the parameter that was originally in the Schrödinger equation. So, but if we want to distribute the energy, We have the radial, see the fact that the radial coordinate of the electron can be changing. We have the orbital, the electron can be orbiting this, so it must have kinetic energy. K, capital K here is for kinetic energy. So the energy of the system can be in the variation of the radius, can be in the variation of the angles by the orbital motion, or can be in the potential energy. That's where the total energy is. Now, if I take this and I put in the radial equation, I can identify, and that's very interesting. I can take out the radial part, because the radial part will be something that has variation of the radius with time, right? The velocity on the radius. So I can easily identify. But I can, what's interesting is I can identify that what I call the orbital kinetic energy is associated with this term here. Is associated with h bar square L plus 1 divided by 2m r square. If you ever learn about things that orbits the other, you know that when you have a mass orbiting a center, you like to characterize the motion with the angular momentum. And the angular momentum square, the angular momentum is r cross p. The linear momentum, right? And the energy of the orbital of somebody, you know, a body of mass m orbiting a force center is L square divided by twice the inertial momentum. And the inertial momentum is the mass times the radius squared, right? That's what we learned from basic classical mechanics. So we identify that the kinetic part of the energy in the orbital part is given by this, and the orbital part must be L squared divided by 2m r squared, which is L squared divided by 2 times the inertial momentum of this mass around the center of force. By identifying things, we came with the value, who is L? L is actually the angular momentum. L is the angular momentum of the orbit, and is quantized as expected, right? The angular momentum is L times L plus 1 h bar squared, the angular momentum square, which is the quantity that conserves in the system. And because it conserves, right, it is a good number to have. So this number L actually is a quantification of the total angular momentum. I could take the root square, and this would be root square of L plus 1 h bar. But giving a value of L, I am giving the value for the total angular momentum. And this is the physical interpretation for this L. It represents the angular momentum of the orbit of the electron in the atom. Very interesting. And we learned that it can have only integer numbers. Therefore, the angular momentum is quantized in the atom naturally by the solution of the Schrödinger equation. Right? So that's the angular momentum is the number L. So each time I give you a value of L for a state, you know that represents different angular momentum. If L equals to 0, means a state that has no angular momentum. How can somebody orbit around without having an angular momentum? Okay, well, this is because if the particle is going that way, and then is going that way, going that way, going that way in a sphere, we will not have angular momentum in average, right? Because it goes everywhere, cancels. So L equals to 0 is the absence of angular momentum in this orbit, and is one of the states we have for the electron in the atom. Normally we give names to the L. When L equals to 0, we call S state. When L equals to 1, we call P state. When L equals 2, we call D state, and so on. Keep going with letters, right? As the angular momentum increases. That's a notation for the state, that's all. If we provide the value of L, we are giving all the information we need. So you see, given an energy, I can have an N. Depending on the N, I can have different angular momentums. Right? And that is one thing I told you when we started this whole course. We started this whole course, I told you that when you have a charge that's orbiting, when you have a charge that's orbiting, which means they have angular momentum, has also a magnetic momentum. I told you this long ago, and I hope you did not forget. So here we have an electron that's orbiting. If it is orbiting, oh, this 4 here is just the page number. Let me put here. If there is an angular momentum, there is a magnetic momentum. I told you this before, and the factor that comes in front is called gyromagnetic factor for the electron. So here we have a state that has an angular momentum. If it has an angular momentum, it has a magnetic momentum. And if you have a magnetic momentum and I put a magnetic field, I will have an energy that's the projection of the magnetic momentum on the field. So imagine you have a field on the z-axis. What is the interaction? What's happening is the magnetic momentum that's given by the angular momentum, we have an energy that is the magnetic moment dot the magnetic field. Or in other words, only the z projection of the angular momentum is the one that's going to interact with the magnetic field on the z direction. That's true for any direction. You are right. But I have to choose one direction. There are some fundamentals in quantum mechanics that I have to choose one direction because of many concepts involved. I have to choose one. So I choose the z, which is the regular one. And because the angular momentum is quantized, so it is, the value of the angular momentum is quantized. The length of this can be only can be only a few values, right? Now, the projection of it is exactly the ml. So the LZ, we can prove, is the ml h bar. But we already proved that the ml can be only some integer values. And now we understand why ml is bounded to vary from plus L when the vector is here, when the angular momentum is fully on the z direction, to when it's fully opposite to the z direction. It is either ml can go from plus L to minus L and can vary in integer unit because the angular momentum, the orbit of this electron, if we can think classically, we can imagine an orbit here, right? Like this. This orbit cannot have any orientation, can only have orientation that gives us an integer projection of the angular momentum. So ml is the quantized projection of the angular momentum. And there are some fundamental parts of quantum mechanics that says that the z component, the total component, are quantized. L squared is quantized because of the small l, and now we see the projection of the angular momentum is also quantized. Right? Okay, so, and that's why we call ml the magnetic quantum number, because this will be fundamental when you put a magnetic field. That's the value, that's the component of the angular momentum that will interact with the magnetic field in the z direction. And therefore, we call it magnetic quantum number. So far, so good. We make a kind of simple interpretation for the quantum numbers, and now we construct the wave function, which is the product of all the functions that I explained to you, we determine. And the angular part can be combined, theta and phi can be, those are the Legendre polynomials, and this is the exponential that comes from the phi, and they combine together to give you what we call the harmonics, spherical harmonics. And normally we represent by epsilon Lm theta phi, this part of the solution. And the radial part, well, the radial part will be the Laguerre polynomials that are polynomials with many orders too. I may show a few for you to see. As a summary of the solution of the atom of one electron, we have a wave function that is spatial, and it exists only for a few numbers that are the quantum numbers, and the state or the wave function is fully characterized if we know the principal quantum number, if we know the orbital quantum number, and if we know the magnetic quantum number. And this wave function square, of course, is the probability distribution in space for this electron. Since it is the probability of distribution of the electron, it's also the probability distribution of the charge, the mass and the charge of the electron. Okay, I'm solving the atom in a very kind of empirical way, so we don't need to expend all our time in details of the calculation, because what we're going to do is use the solution to make interpretations later on in this course. Now, why the atomic orbitals are so important? Well, they are important because they determine all the properties of the system. Right. Every property of an atom depends essentially not on the mass of the nucleus, but depending on the state where it is. This will determine, for instance, how atoms get together, making molecules, making chemical bonds. If they get together in large number, making solids, the way that the wave function of the electron is distributed will determine the structure of the solid, because that will determine how those atoms can get together, and that will give structures. And there are only a few possible structures because there are only a few possible orbitals, as we saw. That will determine the reactivity of the atoms. Normally the reactivity of the atoms depends how the electron sticks out, depending how is the spatial distribution of the electron, because the reactions are basically transference of electrons, combination of electrons, sharing of electrons in chemical bonds. So the way that the electrons are distributed in the atoms determine the reactivity of the atoms itself. And also very important, the distribution of the atoms in those atomic orbitals, which are the solutions. They determine how the atoms interact with external fields, magnetic fields, electrical field, and then we understand very easily why, right? Because the way that the way the charge is distributed will depend on the interaction energy with the external electrical field or magnetic field. So far, we obtain the solutions. We obtain the solutions and we obtain the energies. And the spectral energy for the atom is very interesting because depending on a single quantum number, so the energy depending on a single quantum number, and it goes like 1 over this quantum number square. And of course, when this quantum n is negative, because it's bounded, when I show you the expression of the energy, of the electron in the atom is negative because it's bounded, right? Has some constants in here that's dependent on the electron mass charge, and of course the Planck's constant divided by n squared. And when n grows, this gets closer to 0, which means start to get closer to electron to be free. Here the electron is free. When it reaches 0, the electron is free. We call this the continuous. Then the electron can have any energy. But up to this point, there are only a few states, a few values of energy that are allowed. And those are the states of the atom. And when the atom goes from one state to the other, is what gives origin to the transitions of states. And of course, in most part of the cases, going from one state to the other, we're going to change the wave function. And by changing the wave function, we're going to change the distribution of charge. So when we interact with light, what we're doing actually is moving the charge around in the probability distribution. I'm going to show to you some of the solutions. I did not put the value of the functions themselves, but I can show you the plots. So this is those are the solutions when you have, for instance, L equals to 0. You have L equals to 0. We have a spherical type of shape with some dependence on the radius for the probability distribution. This, what I'm representing here, is exactly psi square. It can either be spherical or can be with those alters. Can be like those little bumps on the side. This is three-dimensional, right? You have to imagine like two little bumps on one side and the other. If L equals to 1, you see when L equals to 0 is fully spherical, and that's the S state. When L equals to 1 is the P state, you see that it's distributed along the axis. And that's why we have two different ML here, because it can be in this X or can be in this X, and this gives you the two different configurations here. When L equals to 2 is the D state. And the D state has this and this tiny little bump in here, as you can see, and those are all the spatial distributions that we can get for the wave. So actually, the wave function, which is the wave that we can accommodate in the Coulomb potential, has all these angular dependencies, as we show here, which creates the orbitals. And inside the orbital, the density is not constant. It may vary with the radius, as we're going to see next. Those orbitals are never in the plane. You know, they are always spatial. Never in the plane as I draw, they are spatial. And you can see in any book very nice configurations of those orbitals. And those orbitals, they determine everything. They're going to determine the most important thing that we have is the interaction of light with the atomic and molecular system. That allow us to see things and everything, which is coming in the next few lectures. Now, this is the angular part, but we could see the radial part as well. When we do the radial part, this is a constant. Let's call the Bohr radius, and the radial part is an exponential type decay, or it is, when I change, this is the n, I'm changing the n, and this is the L. I'm using the notation R and L. And depending on the n, you have different polynomials here for the radial part, and dependent on the L, we're gonna have a different dependence on the exponential too. Right? And the probability distribution, what I draw for you at the transparency before, where the overall distribution is space. Now I'm just taking the radial, and of course the probability, because it has this 4 pi r square dr integration, the density of probability is r square times the r of nl, and plotting that, we see that actually on the radial part it looks very much like a wave, right? Looks very much like a wave. And those are the solutions of the atoms. You have oscillations on the radial part, and spatial distribution depends on the angles too. And that creates what we call the potential, the atomic orbitals. The atomic orbitals is very important, and we had to show that what are the atomic orbitals? Are the representation of the waves that are allowed to be accommodate matter waves, waves that represent the electrons that are possible to be accommodate in the Coulomb potential. That's it. You know, when we have a box, it's easy to see what wave can we accommodate. But when we have a potential like the Coulomb potential that has a divergence at the origin in r equal to 0, right? It's not so trivial, and the Schrödinger equation is going to give us the possibility of those waves. And those waves square is the density probability. Therefore, it's also the density probability of charge and mass. And we will determine all the properties of the atomic system, as we're going to see in the coming few lectures. Well, we're going to use this, we're going to argument things like this, but we're not going to come with the solution all the time for this, right? But you have to understand that the atomic orbitals is the waves that comes from the quantum origin of the electron in the atom. Because this is a quantum system, you cannot have any direction. The electron cannot be actually orbiting like classically. It is distributed following some numbers, following some quantities, the angular momentum, the projection of the angular momentum, and the energy, the principal quantum number. We have to add more things to the atom to be more realistic. But this is only a course that wants to give you the fundamentals, so we can easily make interpretations. So we're not going to go to the relativistic corrections and things like this, but whatever we needed to explain that, to explain some phenomena that happens in biomedical or any other engineering application, we're going to do. Okay, I hope you had a good idea what are the atomic orbitals, what the origin of them. They are just the electronic waves around the nucleus, right? They are the waves allowed by the quantum mechanics around the nucleus, and therefore they have a special spatial configuration, and it's not any configuration. It's the one that's determined by the principles of quantum mechanics. Okay, see you next lecture.